All right, hello everybody. I'm coming to you today from the interior of the sound booth in the phonetics lab here at the U of C. That's why it may look a little bit dark and scary in here. If you're curious, here's the phonetics lab in all its splendor. We got our recording set up there. Tana's been working on something for her honors thesis. There's also the phonetics library, such as it is back there, but it doesn't matter because we're here today to talk about analysis of variance, or we're going to start with one-way ANOVA. So analysis of variance is abbreviated ANOVA, and the most basic form of it is the one-way ANOVA, which is what we'll walk through today. And I've got a lecture which is about 36 slides long, and normally a lecture that long I would like to split up into two. I'm not sure if I'm going to have time to get through all of it in this particular sitting, but the goal is to get through all of it, so it might be a bit long, but there's a lot of R code in the middle, so it may just be kind of, expansive without there being too much content. But either way, let's get into it. And I will preface this as well by saying that I don't have anything fun to offer you today, aside from, all the recording equipment in the phonetics lab, but you're not here to share it with me, but maybe someday, who knows. So anyways, let's just get down to business. So we're going to work on analysis of variance. Like I said, this is abbreviated as ANOVA. And I guess the one kind of jokey thing I could say is that over in Britain, they call it Anovar with an R at the end. So hopefully you can see, but it's analysis of variance. So the N from analysis, the O from of, and the VA for variance. At least that's how we say it here in the North American side of the English-speaking world. But in Britain, they can put the R at the end there because it's still ANOVA, right? So there you go. Maybe that's funny. But we don't say ANOVA, just like in America or Canada, we don't say champagne supernova either, but some people do. Anyways, you've decided to analyze variance. Do you remember what variance is? This may be the last time I ask you this question, but I've asked it at least 3 or 4 times by now, maybe 5. I don't know. Who's counting? Because this is a stats class. Why would we count anything? What matters is not how many times we've done it, but what the answer is. So variance, as you might recall, is the sum of squares divided by degrees of freedom. And with repetition, I've said this enough times by now that hopefully when you see quantities like this, which you will see in the output of the ANOVA commands that we use in R, they will have some meaning for you, or they will look somewhat familiar. So we're going to do a lot of tabulation of sums of squares. We're going to have to think about degrees of freedom, or at least that's how the process works. Again, usually when we actually run these things in R for our own research, we just kind of care about the output at the tail end, whether it's significant or not. But this is how we're going to get there for this particular method. So I've also got a question about, do you remember what degrees of freedom are? And again, we can think about their definitions in terms of like the number of, statistics or quantities in the calculation of a statistic that are free to vary, that sort of definition. But what you might recall more specifically is that when you're dealing with samples, the number of degrees of freedom is usually n-1 because we're normally calculating, say, the mean of some sample, and everything else except for one of the other sample item values is allowed to vary freely. But once you get to that last one, you know what the value is going to be because you already know the mean, so on and so forth. Normally in samples, degrees of freedom equals n-1. In populations, though, it's the real world, so all the items' values can vary freely. So you get normally a degrees of freedom of n, the number of all the items in your sample. But anyways, that's just a refresher. Another refreshing question, hopefully, is do you remember how we test whether the variances of 2 samples are significantly different from each other? And I'll pause here because we did this kind of briefly way back when, several lectures ago before we got into the whole regression thing. But then it kind of came back at the tail end of the regression discussion because the way we do this, which hopefully you now remember, is that we run an F test, or what I called a variance test when we first got into it. So we can use an F test to evaluate the value of the ratio of the variances in the F distribution, which you might recall is this not normal looking distribution, which has kind of a clump, or it's kind of clumped together between 0 and 1, then it's got a long tail. And kind of the goal of an F test is to see whether or not the ratio of 2 variances is different from 1, either on kind of the short end or on the high end, as it were. In this example, or basically in this technique of analysis of variance, we're going to be focusing on sort of the long tail end of the F distribution, because we're going to be focusing on whether sort of the variance we can predict in the value of some variable is going to be larger than the variance that we can't predict, or the random variance in the value of that variable. So in Anova's, we're going to run F-tests to see how variances compare with each other. I've got the last warm-up question for this lecture as the question is, which variances are we going to look at? And I kind of already gave away the answer there because, like I said, this is a bit of a lengthy lecture and it goes through a roundabout way to get to the answer to this question. So I'll give it to you right ahead of time. And basically, we're going to look at the variances of what can be predicted in the variable of interest, how much variance can be predicted in that variable of interest compared to how much variance cannot be predicted in that variable of interest, using some independent variables that we're trying to use to predict the value of that dependent measure, as it were. So that may not make sense at this point, but again, the ultimate goal is here, we're just going to be comparing variances, sort of predictive variance versus random or error variance against each other to try to figure out if they're significantly different. Okay, so ANOVA is used in cases when the dependent measure is gradient and the independent measure is categorical. And we've actually been kind of working with cases like this before. Before we got into regression analysis, we did this for, say, t-tests, even if we didn't make it explicit. But this is just like a t-test scenario, except the ANOVA will allow for more than one independent categorical factor. So you can say before we were looking at t-test scenarios where, like, is the VOT of speakers from Calgary different from the VOT of speakers from Edmonton? Something kind of inane like that. But in ANOVA, so that's basically as far as you could go with a t-test, but in ANOVA, you could throw another factor in there, right? So you could also say, well, I'm going to look at whether it matters if they're from Calgary or Edmonton, but I'm also going to look at whether they're male or female speakers. There's two potential factors that could feed into this. And then on top of that, there can also be more than two levels within any of those categorical factors. So we could look at, say, does VOT depend on whether you're from Calgary, Edmonton, or Vancouver? So for that simple factor alone, we could look at more than two levels, as it's called, basically contributing to the amount of VOT you get from any individual speaker. And I guess if you wanted to play around with the gender factor as well, in the modern day and age, we could talk about people who don't fit into that binary split between male and female. So we have like more than two levels there potentially as well. But either ways, there's factors on one hand and then there's levels on the other. And I'll explain what that means again as we get into this. I'll walk you through the terminology, so hopefully you don't get confused. But just before we get there, I'll say the Anova approach itself becomes identical with the t-test approach when there is only one independent factor that has two levels. So that's the case where you say, I'm just going to look at how does VOT depend on whether or not somebody's from Calgary or Edmonton. I could run a one-way Anova for that sort of statistical setup, or I could run a t-test. But in fact, if I run a one-way Anova for that sort of analysis, it winds up being the exact same thing as running a t-test, comparing Calgary versus Edmonton or any one-on-one comparison for a dependent measure. It's the reason we're learning Anova, though, is because we can expand it in sort of both those dimensions, both including more than one factor as a contributing factor to the dependent measure, or a factor with more than just two levels in its number of sort of parameters or number of options to vary in, I guess you could say. I stumbled over that, so I should probably stop talking. Like the title of this slide says, actions speak louder than words, and you're probably going to remember or most want to know how to get this to work. So let's try an example. And like I said, we're not going to look at just sort of this same sort of setup we could do in a t-test, even though that's valid for ANOVA. But I want to look at an example where we're going to kind of figure out whether sort of one of three different contributing options can have an effect on the dependent measure that we're going to now analyze in our data setup. So we're going to start by going back to the VOT data we collected at the start of the semester. And like I said, there's a lot of R code in this lecture, and hopefully I'm not spitting through all of it too quickly. Oh, I was a little worried there that the internet wouldn't work here in the booth, but it does. So problem solved, or problem averted. And what I want to look at here is this is the VOT data that we collected back at the start of the semester. And I want to look at a particular speaker who's actually not in this class, still working through the PhD program at this university, but he took this class 2 years ago, and his name is Dusan. And he is a native speaker of Serbian who speaks English very well. And kind of the question that we want to find out the answer to is whether or not the VOT for his stops with these English words depends on the place of articulation of those stops. So we've got 3 different types of stops, P, T, and K. We've got VOT measures for all of them. We've got a whole bunch of other measures here as well for F0 and like formant values and his height, all that stuff. We're not going to worry about that for now. We're just going to look at VOT and see whether or not it depends on which stop is being produced. And I think you might already know the answer to this question before we get into it, but I want to show you how Anova will answer that question. And I will point out once again that we're looking at one factor here. This is the independent factor or independent measure. It's called stop. This is the dependent measure of VOT. We want to see how VOT may or may not depend on stop, place of articulation. And then stop itself has 3 different levels in it because there are 3 different types of stops. So P, T, and K. So this is kind of analogous to that situation where I was mentioning before, like the less scientifically interesting question, or maybe it's more scientifically interesting. I don't know. But does VOT depend on where speakers are from? Like we could have 3 different levels within the one factor of origin. So like Calgary, Edmonton, or Vancouver, something like that, right? Okay, so getting back to the main question at hand, our big question is, does mean VOT differ among the 3 places of articulation, P, T, and K, just for this one speaker, Dusan? And what I'm not asking by asking that question is, does the mean VOT of P differ from the mean VOT of T, just that alone? Or does the mean VOT of K differ from the mean VOT of P? But overall, does VOT change depending on the stop being produced? So you can think about this with 3 different levels in our factor. We could just compare any 2 of those levels to each other. And like I say, run a t-test, sort of comparing the VOT of P versus the VOT of T. Hopefully I said that right. So P versus T, that sort of thing. But we're not going to do that. We're just going to throw all 3 of them in there at once and then say our null hypothesis is that the mean of P is equal to the mean of T, which is equal to the mean of K. And then it doesn't make any difference if you're producing stops at one place of articulation or another. They're all across the board the same. Okay, that's our null hypothesis. If we get a significant result for this test, that means that these 3 things are not all the same. It doesn't tell you specifically which 2 are different from each other or if all the 3 are different from each other. It just says this doesn't fly anymore or this doesn't work. We can't assume that all of them are equal. We have to take, in this case, place of articulation into consideration. Okay, so that's the basic sort of conceptual setup for how VOT works. This slide walks you through the terminology, which I've kind of walked you through already, but we have VOT in this case being the dependent factor. We have place of articulation, or if you want, stop type, being the independent factor. So like I said, we're going to investigate how VOT may or may not depend on stop, place of articulation. The factor that we're looking at has 3 different levels. So the levels are P, T, and K. You could also think about that if it helps you, if we're just looking at like, say, how age affects VOT or something, or like formant frequency or something like that. You could look at, say, like kids, adults, old people, something like that. Those would be 3 different levels for that factor of age, what have you. When an ANOVA has only one independent factor, it is called a one-way ANOVA. And like I said, we're doing this to start off with because it's the simplest case. We're just doing it in a way that's a little more complicated from a t-test because we have 3 levels of our factor rather than just 2. And then if we want to add another factor to that, like say if we're going to add, say, gender, or in this particular case, like city of origin or something like that, then we ramp up the number of ways we're looking at in the ANOVA. So an ANOVA with 2 independent factors would be a 2-way ANOVA. And we're going to save that for next time because once you get 2 independent factors, you have to worry about how they might interact with one another. For now, we just have one factor. It's got 3 different levels, and we want to see if VOT depends on these different levels, these different stop places of articulation. Okay, hopefully that's clear. The other thing we're going to look at or have to worry about is basically looking at kind of two ways of modeling the variance in the dependent variable we have in this setup. So our method is basically going to try to determine whether we can significantly reduce the amount of variance by assuming that part of that variance is due to a change in stop place of articulation. Actually, I might expand on this a little bit and then say we're trying to see if we can significantly reduce the amount of variance in the dependent measure or the dependent factor by assuming that part of that variance is due to a change in stop place of articulation, i.e. the different factor levels. So we're going to create two models of the total variance, one pretty boring, one less boring, and then see whether the more complicated or less boring model buys us a meaningful reduction in the overall variance. Okay, so the boring model is model number 1, and for this one, we're just going to calculate variance in the usual way by considering all of the data points for the sample in question with respect to the entire sample mean. I've already asked you what variance is. We've answered that question hopefully many times in your head, just because you took this class. So we don't have to sort of worry about how to answer that anymore. We can just remind ourselves that we have this equation for the total sum of squares. This is the part that's on the top of the equation for variance. It's the sum of the squared differences between the individual observations of a data set and the mean of those observations. So our dependent measure here is going to be called y. Hopefully makes sense from the way we were drawing linear regression graphs. Y would make the dependent measure y, but that's what it is. So the mean of it is y bar here, and these are the individual observations. We're going to just go through the entire set from I equals 1 to n, and then square those deviations from each other. Our degrees of freedom, assuming this is a sample, we're just going to make the degrees of freedom n minus 1 because we have this one kind of set statistic in it. And then our variance is going to be that equation, right? Sum of squares divided by the degrees of freedom. This is the boring model of variance. It's just taking all of these as, it's the more democratic model of variance because all of these are basically the same. They're just individual observations. They all count the same. There's nothing especially different about them. The more complicated model or more interesting model is going to divide the variance up into two potential sources of variance. And this is going to look a little bit like what we were doing with linear regression. So we have, on the one hand, the variance due to the differences between the factor means, or what is called the treatment means in Anova terminology. And we're going to call that the treatment sum of squares. So basically, we're going to say that for each of the different levels in our independent factor, the mean value of y might change. And we're going to calculate how much variance we can account due to those factor changes. And we'll call that the treatment sum of squares. Like I said, we're borrowing from medical terminology here because I guess medicine is more important than linguistics, because if you screw up in medicine, people do actually die. So they got to get things right in a way that we don't have to. But still, this is the way they're thinking is, oh, if I give this person medicine 1 versus this person medicine 2 and that person medicine 3, like how much does it affect like how sick they are, that sort of thing. We're not thinking in terms of treating somebody. We're just analyzing what they do with different stop places of articulation, but still we're going to use the same terminology. Anyways, this first part is sort of the variance that you can predict based on the independent factor level. This is sort of the predictive variance here. That's our first potential source of variance in the overall variance. And then the second part of that is the variance left over within each factor level or treatment. So this is the residual or error sum of squares. We're going to be able to account for some of the variance, hopefully based on the changes in these factor levels. And then there's still going to be some variance left over that we can't account for. And we'll just say that's, noise. That's the residual error deviation, and we can total that up to get a residual sum of squares. But basically, this is sort of the signal. This is the noise. This is the amount of variance you can predict in the values of y. This is the amount of variance you can't predict in the values of y, at least given the model that you're playing around with. Okay, so going back to the first model, these are the two models we'll compare. The boring model is the null model. And in this case, we're saying the place of articulation of the stops doesn't make a difference to VOT. Okay, so we've played around with this sort of stuff in the past. We can just take a look at what we're dealing with here and say, well, the mean VOT for Duchamp of all of these measures here in this column is 68.6. That seems like a nice, good average value for VOT. It's also a nice good average value for temperature in Fahrenheit, but we won't go there. It would be about 20 degrees Celsius. In this case, it's just 68 milliseconds. If I look at the variance in Duchamp's VOT, I get this measure, 1421, which doesn't really mean a whole lot to us. But the way we get there, again, is using that equation. I'm just looking at how much the individual observations of Duchamp's VOT differ from the mean value of Duchamp's VOT. I square those deviations, and then I add them all up. And I get a total of 19,898 whatever units, milliseconds squared, I guess. It doesn't really matter because then we're going to divide that by the degrees of freedom. There's 15 total observations. I didn't make that explicit, but there's 5 observations for each place of articulation, so that's 15 total. That makes our degrees of freedom 14. And if I divide this sum of squares by those degrees of freedom, lo and behold, I get the exact same value of variance I did the easy way, just by using the variance command in R. Okay, so that's where we stand. I might actually keep score here. Hopefully I can get away with this without too much difficulty. But yeah, let's look at this in an Excel spreadsheet just so we don't have to go up and down all the time here. And I'll make this a little bit bigger so you can see it better. But this is, we'll call this the total, and our mean is 68.6, and our variance is, actually, I'll do this as well. This is a big number, almost 20,000. This is a smaller number because of the degrees of freedom. And actually, maybe I'll do it this way. We know the degrees of freedom overall is 14. And I'll just save this here to my desktop. So, sorry. I will definitely edit that out in the final product. So I'll mention one thing here, which may be slightly amusing, maybe slightly annoying, but we talk a lot about sums of squares in Anova, and it's abbreviated often as SS. Okay, so that has nothing to do with Nazis or anything like that. It's just an unfortunate coincidence. Sorry about that. But that's what that means right there, and that's why I'm abbreviating it like that. We'll come up with a different term for variance here as we go, which will look kind of similar. Okay, so what I want to do here is to give you a graphical sense of what this sort of null model variance looks like. And we're going to learn some graphing tools as we go here because, like I said, there's a fair amount of R code in this lecture. So what I will do to make our lives a little bit simpler, having already kind of stored away the mean and the variance for Duchamp's measures, is I'm going to just plop his VOT measures into an array called VOT array. So this is just the VOT measures by themselves. It's this column in the original data frame. Okay, so what I want to do is plot those data points. And I'm going to use this command, which involves a number of sort of parameters that we haven't seen yet. So 1 through 15, this is the, when you say plot, it's just going to create a scatter plot. And the 1 through 15 part just says go for the x value, have it range from 1 to 15. And for this, which it tells us what the y value is for this scatter plot, it's just basically saying go through the VOT array values in order from the 1st to the 15th, and then plot those alongside x as it goes from 1 to 15 in value on up the scale. This means don't put any label on the x-axis. This is the label on the y-axis. This is the labels on the little tick marks on the bottom for x. I'm going to do something with that later. And this cycles through colors. This is actually kind of a neat command. I just found this on the internet as I was putting together this lecture. But this basically says cycle through colors 1 through 3, doing 5 at a time. And turns out the 1 through 3, those colors will be black, red, and green. Yeah. And this last bit just says fill in the circles when you make this plot. So I'm going to plot this, and it looks like this. So here are my P's in black. These are my T's in red, and these are my K's in green. And they're not mine. They're Duchamp's. But you can kind of see it looks a little bit linear here. But we're not going to do a regression analysis per se on this. We're just going to try to figure out whether sort of the different colors matter here, right? So whether the different places of articulation matter to the value of VOT. and there are no labels down here. So I'm actually going to have to fix that. And I'll do it using this axis command. So this axis or the one here within the axis command says do this to the x-axis, which is the first axis in this formulation. And I want to put it at tick marks 1 through 15. And what this stuff is going to do is it's going to paste together p's with the numbers 1 through 5 as it goes. So it's going to just glom p with a 1, and then p with a 2, then p with a 3, so on and so forth. For the next 5, it'll do t1, t2, so on and so forth, and this will do k1, k2, so on and so forth. It's easier to see than it is to say, so I'll just hit return there, and you can see all I've done here is add these labels down here on the bottom. In case you should ever like to do something like that yourself, now you have the code for it. Okay, we're not dwelling on this stuff yet, though. We're just trying to get a sense of what this variance looks like. So I'm going to plot the average VOT value here for Duchamp's data, and I'll explain how this works as well. So when you use the lines command, I think we've seen this before when we were looking at residual error in the regression analysis. It's the first bit here before the comma is the values you plot for x. And then this stuff is the values you plot for y. And what this is doing is basically saying start at x value 1, and the y value is the mean value of Duchamp's VOT, and then end this line on x value 15 and y value of the mean value of Duchamp's VOT. So the y doesn't change at all. It just plots it, the mean value of Duchamp's VOT from 1 to 15, going horizontally, basically. This is going to make it a dashed line, and this is going to color it blue. I hit return, and lo and behold, it does everything I said it would, because I tested this multiple times before I recorded this lecture. But here we go. Here's the mean value of VOT for Duchamp. And what we're trying to look at here is just the variance. So variance is just kind of a measure of how spread out these dots are from this mean line here in the middle of the whole business. So the last thing I'm going to do is plot lines connecting each data point to that mean VOT line. And I can do it like this. I'm just going to run a for loop. So I'm going to do this 15 times. And it's going to say start at x value I. So first x value will be 1. And then the y value will be the mean, that blue line we just plotted. And then it's going to end the line still at the same x value, but then it's going to plot that line out to the individual data point that is in the VOT array. So this will draw vertical lines between these two y values. It's going to color them blue as well. I'm not doing this, so it's going to be a solid line, and we'll just hit return, and this is what it's going to look like. We're going to see these blue lines extend out from the mean line there out to each data point. And I'm just doing this so you can see this graphically, but these blue lines are the variance, basically. This is how much the data varies around this mean. And in some cases, it's larger. In some cases, it's lesser, right? But that's kind of where we're getting at graphically. Okay. And I've got the same graph here because, like I said, I tested that, but I also wanted to put it in the notes in case you needed something to refer to. But basically, the total sum of squares is the combined length of these vertical blue lines. We already calculated all this stuff. So these are the total sum of squares, and I divide those by the degrees of freedom. I get this sort of average length of the blue lines, which we'll call the variance, right? Okay, nothing here should be new other than the graphical depiction, basically, but hopefully this should all make sense. Maybe it just makes sense in a slightly different way now. Let's move on to Model 2. Model 2 basically posits that stop place of articulation matters to the amount of VOT we get in each data point. So in this model, we just have this mean, and you could maybe think about it like maybe Duchamp is just sort of targeting this mean VOT whenever he produces a stop, and then he just kind of randomly makes errors on either side of that mean value. But it doesn't really matter whether he's producing a P or a K. It's just, there's some random error in there. Model 2 is not saying that. Model 2 is saying that maybe we're going to get different targets, say, for different places of articulation. And that place of articulation will therefore affect the amount of VOT we get in each data point. So we can start building this model by first splitting up Duchamp's data into 3 separate subsets, one for each place of articulation. And I've just got this in here more for housekeeping purposes for R. Hopefully this should all make sense and not be too confusing or complicated, since you've done a lot of subsetting of data by this point in R. So I'm just going to split it up into the P's, T's, and K's here. And if you really want to look at it, that's what it looks like. But you've kind of seen that before. I also want to do this, I guess, a little bit for housekeeping purposes, just to get a sense of what these values are. But we'll look at the means and the variances. And I normally do this in class on the board, kind of as a way to keep score and give people a reference frame for what's going to happen next. But I'll put these numbers up here if I can. Yeah, so for the P's, we get a mean of 40.86. For the T's, it's a little bit higher. For the K's, it's a lot higher. And I've got variance values here as well. I'll just put these here without calculating what goes in the middle. And I'll let you think about what might go in the middle before I get there. Yeah, but if you look at this, it's interesting, right? So our overall variance is 1421. If we split it up, like we got 1,000 for K, we got 680 something for P, we get 260 something for T. It looks like if you add all these up, after you split them up, it looks like it's going to be bigger than the variance just by itself. So, what does that mean? Don't know exactly yet. We already figured out the variance for everything, so I'm not going to do that again. But just kind of keep that in mind. That's just what we get from splitting up the whole data set into 3 places of articulation. But now we want to split up the variance into what we can predict and what we can't predict. So for this individual factor level / treatment data, we will calculate 3 separate sums of squares, one for each factor level subgroup. So I'm going to do this in R again as well. I've got what I'm calling Duchamp's P sum of squares. So this is just looking at sort of the differences between the individual observations and the mean values for a particular place of articulation. So before, when we calculated variance way up here, we were just looking at this without any regard for different places of articulation. We just got a mean value for the whole set. And then we looked at each individual observation by itself. But over here, we have to take place of articulation into account. So we have to do this individually for the P's, T's, and K's separately. And then for the mean of the P VOT, we only consider the P observations here. And we'll do the same thing for the T's and K's later on. So this gives us 3 separate sums of squares, like that, and like that, and one more for K, like this. So we can look at this by itself, and now we have that sum of square information that I was glomming over before, and we'll just put it in right here for safekeeping. But now this is starting to look a little bit smaller, right? So over here, when we looked at variance, this looked bigger than the overall total. But now we have like 4,000 plus about 2,700 plus about 1,000. If we add that all up, we get what's called the residual variance. And it's 7,900, 7,911.764. Yeah, so I could do that in Excel as well, I guess, but it's smaller than this total sum of squares. And the way we get from the sum of squares to the variance is by dividing by the degrees of freedom, right? In each case is going to be 4 because we have 5 repetitions of each of these stops for Duchamp's data. So that's kind of, you wind up dividing by a smaller number than overall than 14. That's kind of why this changes a little bit, but that's besides the point. The point I wanted to make is that if you add this whole thing up for the residual sum of squares, and maybe I'll do that here and put it in the spreadsheet as well, you get a smaller number than the total sum of squares up here. So 7,900 is smaller than this, which is almost 20,000. Here's the point. You will always get a residual sum of squares that is smaller than, maybe equal to, the total sum of squares, but it's never going to be larger. The total sum of squares is all the variance you have to deal with. And this is just sort of the amount of that total sum of squares that we haven't figured out how to deal with yet, at least not based on place of articulation. That's the amount we have left over. But we're going to be able to predict some of this variance based on our independent factor. That's kind of the point. But for now, our residual sum of squares is the variances left over after we take those place of articulation means into account. Okay, so I want to take a look at this. It's going to look similar to what we plotted before, but I'm going to get rid of this guy. Sorry to see you go, but it's okay because you're in the notes. I'm going to use some of the same commands I used before, so we don't have to worry about this too much. At this point, we're where we started with the labels and the dots. But now I'm going to plot separate means for each place of articulation. So the first one's going to be black because those are the P colors. And I'm just plotting the mean of Duchamp's P VOT. So I have a black dot or a black line in here just for these first 5. And I'm also going to plot the deviations of those individual observations from that black line. But again, I'm only going to consider the observations for P here, right? Because place of articulation matters now. So there we go. These are our deviations for P. This is the variance we cannot account for in P if we take place of articulation into account. Okay, and then again, this is going to look similar in the slides because I wanted to keep it here for safekeeping. We've walked through all these numbers as well. Degrees of freedom is 4 again because we have 5 observations and 1 mean. So 5 minus 1 is 4. And we get a variance of 689 out of that. And all I'm going to do in the next slide is the same thing for T and K. And we'll see what the final finished product looks like. But we're basically going to get a red line for the mean of T. And then we're going to get these other lines spreading out from T to the observations for T. And then we will get the exact same thing for K, both the mean line and the line stretching out to the observations, but these will be in green, not red. And just to prove to you that that's what I'm doing, I'll show you the graph again. So we've got sort of the variation here, or the variance we can't account for P, the residual variance. It's in these vertical black lines, then that residual variance for T with these vertical red lines, and the residual variance for K in these vertical green lines. Yeah, so I'm going to do this again, but we can kind of look for a second back at what we had here in the boring model, the null model. And these are all blue lines, but basically what we're thinking of here is how these lines, these vertical lines compare. This is not the exact comparison we're going to make, but we're trying to reduce the size of these vertical lines in this graph. Sorry, we're trying to reduce the overall size of these vertical lines from this graph, and they should look smaller over here just by taking place of articulation into account. And it kind of looks like that's what we're doing, right? So these blue lines here look, generally speaking, bigger than the different colored lines we get here. But we don't know for sure yet because we haven't quantified it. Like I said, though, it's always valuable to both look at a picture and also try to quantify what's going on in your data so you can kind of get both perspectives on it. But this is where we're at. The residual sum of squares for these 3 different places of articulation. It's the total length of these vertical black, red, and green lines. We've seen these numbers before. They're in the Excel spreadsheet, so we don't need to walk through them again. But that's what that amounts to. Okay, pause. What are we going to do next? We're going to add all the sums of squares of those individual factor levels together to get the residual sum of squares. And I think I did that. Yeah. So what we do with this residual SS, which is about 7,900, is that we divide it by the degrees of freedom to get something called the residual mean square. So that's the answer here at the bottom of this slide. I kind of walked through the rest of it a little bit quickly. But we're going to get a value of 659 here. And I want to make sure I walk you through the math before I get too far ahead of myself. So we know what we got here. These are the overall sum of the lengths of our black, red, and green lines. And the way we tally that up is with this equation, right? So we're using a little bit of new terminology here. We've seen this summation sign where we go from I equals 1 to n. That's just the number of observations in each data set, n being the number. the total number, but we've got new notation here. So we've got embedded summation signs where the outer one goes from j equals 1 to k. And k is the number of levels in my independent factor. So when I have a notation over here like y bar sub j, that just means this is the average or the mean value of VOT for one of my factor levels like p. That would be j equals 1. When we move up to j equals 2, that is the mean value of the t VOT, so on and so forth, until I get to k, which is 3 in this case. It's the number of levels I have in my factor. So j is going to range from 1 to k, or 3 in this case. You also have to add together the degrees of freedom for the different factor levels. There's 4 in each case, but you can use this equation to do that. So just summing from j equals 1 to k, or 3 times, add 4 to each other to get 12. And that's how I get this mean square construction, or variance is how we normally call it. But that, like I said, as promised, we're coming up with a new term for variance here, which is mean square, or MS. And I guess I can make this a little bit bigger. Yeah, so if you see that, that's where that comes from. And that's kind of a nice way to think about variance as well, I think. It's just sort of the average length of these deviations in this particular case. After you walk through all this other math on top of it, so dividing the sum of squares by the degrees of freedom. Okay, so that's the residual mean square. And I'll put that here. So that's 659.3137. And I'm going to bold that, actually, because it's going to matter later. Not that all this doesn't matter, but this stuff matters in particular, because it's what we're aiming to get as we analyze what's going on with variance here, because we're doing analysis of variance. Okay, so there are 2 ways to calculate what is called the treatment sum of squares. And as usual, I'm going to do it the hard way first and then show it to you the easy way at the end. But the less efficient but more explicit way is to calculate the sum of square differences between the treatment means and the total mean, multiplied by the number of observations within each treatment. So this is another wordy way to express this. Here's perhaps frightening way to express this, but I'll try to walk you through it so that this makes a little more sense. So we're going to calculate the treatment sum of squares. And remember, when I'm talking about sum of squares, I'm just looking at sort of like summations of deviations between 2 values. And in this case, the deviations that we're squaring is the difference between the mean VOT value for any individual place of articulation from the overall mean VOT for the entire data set. So if you remember, just to give you a numerical example, our overall mean, our y bar, is 68.6. And like an individual place VOT mean would be like P has a mean of 40.86. So when I'm looking at my first y bar sub j minus y bar overall, I'm looking at 40 minus 68. And then I'm going to square that deviation. And then kind of the interesting part, which may not be intuitive, is that in addition to squaring that deviation for like one place of articulation, I'm going to count it 5 times, because I've got 5 different observations for that individual place of articulation mean. So I'm switching the order here a little bit. You can think of it either as multiplying by n or just adding it up n times. But I'm going to walk through the different factor levels, looking at this sort of calculating this deviation between the levels mean and the overall mean, squaring that, and then adding it up n times. That's what the double summation means here. I've got a question here about how many degrees of freedom do we have for this equation. If I had a little more time on my hands, I might pause and wait for you to answer that. I think you've seen the answer before, though, because in this case, our degrees of freedom is going to be k minus 1. Or in this particular case, it's going to be 2 because k equals 3. That's how many levels we have in our factor. So keep this in mind, because this will become relevant later. But we're going to calculate the treatment sum of squares, ultimately dividing that treatment sum of squares by 2 to get the treatment mean square. Okay, so what the treatment sum of squares is calculating is basically how much variance we can account for by just looking at the difference between the overall mean VOT and the mean VOTs for the individual places of articulation. And then in addition to that, we do that for each data point. And this is another case where it would probably be easier to understand if you just look at what's going on rather than reading all these words on a PowerPoint slide. But I want to reiterate something I said before here, which is that when I'm coming up with this measure, what I'm trying to measure is how much variance in the data I can predict based on place of articulation alone. That's what I'm counting up here. Yeah, so let's take a look at that, how much that variance is. Again, I'm going to recycle some of these old commands, and I'm going to get a plot at the start here with just the data points and my labels on the bottom. And what I want to do is draw in a line for the overall mean VOT, which we've seen before, this blue line at 68.6. But I'm also going to draw on lines for the means of the individual places of articulation. So we've seen these before as well, but just not on the same graph. So I've got the mean value of P's VOT and the mean value of T and the mean value of K. And I'll show it to you on the same graph because the whole point of this is to take a look at it. But we've got our individual places of articulation means and the overall mean here. Yeah, and so for each place of articulation separately, what we want to tally up is the total distance between the overall mean and the individual places mean VOT. Right, so I'm going to be linking up the various dashed lines here and seeing how big those deviations are, basically, when I calculate this treatment sum of squares. Yeah, so we'll do it first for the P data. And like I said, for each of the 5 observations of P, I'm calculating the deviation or the distance, the length between the overall mean and the individual place mean. That is what I'm doing in an equation like this y bar sub j minus y bar overall. I'm getting this measure and I'm doing it 5 times. Okay, like I said, the idea here is this is how much variance you can predict. Or if you're going to make a prediction based on place of articulation, you're basically making this prediction that VOT is going to be here for P. And so that's how much you kind of gain from your null model, which says that overall you're just expecting VOT to be here in the middle. But you get a little bit of a bonus here, potentially, by shifting the whole VOT expectations down for P. Yeah, so note that we're effectively predicting the same effective place on VOT for each observation within a place of articulation. So we wind up adding the same value into the total for the treatment sum of squares over and over again for each data point. With the sort of residual variance, like it varies by each individual data point just by nature, right? Because we can't predict that, so you're going to get a different value each time. But the predictions are consistent, right? That's why they're predictions. So we have to count them 5 times there. I'm going to draw on the same lines for T and K. And hopefully you're still with me at this point, but they're going to look similar. As you can see, those are the ones for T, and here are the ones for K. And at this point, we're still doing this graphically. I'll show you what the calculations look like in a second. But here's our finished product for these. We're getting different size red, green, and black lines here. And this is what it looks like in on the PowerPoint slide. I've also got some numbers here, which we haven't seen before, but they're the treatment sum of squares for the 3 different places of articulation. And as long as we're here, might as well sort of add those up and plop them into the Excel spreadsheet that I'm playing along with. So again, for P, I'm taking the overall mean. I mean, I guess I'm doing this a little bit backwards. According to the equation, it should be 40.86 minus 68.6. I apologize for that. And then square that. It winds up being the same thing because you square it. So the overall squared value will be the same, but I should be consistent so that I don't confuse people, namely people who are trying to learn like yourself. So I'll get rid of that, sorry. And I wind up getting the same overall summation totals regardless. So for P, if you total up the lengths of these 5 lines, you get 3847. For T, you get a smaller value. You can see those are smaller. And for K, you get a bigger value because these are bigger, right? Overall, if you add those all up, you get 11,986.36. And we already know that our degrees of freedom are 2 because I already told you the answer to that question. Maybe you answered it yourself at home. Either way, that's what it's going to be, what its value is going to be. And based on these two values, we can calculate the variance or the treatment mean square. I'll show it to you as well, the clunky R way, because otherwise you're just taking my words for granted there. But this is the same sort of calculation here, like subtracting the mean of P's VOT, or subtracting the mean overall VOT from the mean of P, so on and so forth, squaring it. If I do that for all of them, I should get the exact same value, 11,986.36. So yeah, that's what I said here, right? So that's how you do that. And I'll point out that the easy way to get this total, interestingly enough, is to subtract the residual sum of squares from the total sum of squares. So actually I'll do it this way, not that way. Oops. Do I have a value? Yes. So no, I don't know why that happened, but we'll try it like this. Yes, it just didn't like some code, hidden code there in the Word document or PowerPoint. But here's the point of showing you this. So remember, my total sum of squares was just the variance as I normally calculate it, 19,898.12. My residual sum of squares is this. Turns out that this plus this equals this. So again, we're calling this treatment and residual sum of squares here. But another way to think of this is like this is predicted and this is error. Or this is signal and this is noise. And if you remember, based on what we talked about with all that math with R and walking through the regression analysis, overall variance, since these two guys don't correlate with each other at all, overall variance in some variable can be split up into the predicted variance and the error variance. So these two add up perfectly to the total sum of squares. And again, we're just trying to compare how much variance can we predict versus how much variance we can't predict. So we'll calculate the treatment mean square and then use that in our F test in comparison to the residual mean square. So what we get for the treatment mean square is this value. And I'm going to bold that. So this is just 11,900 whatever divided by 2 is almost 6,000. And I'm going to compare these two values. So this again is my predicted value, or my treatment mean square. Put it like that. And this is my residual mean square. These are the two variance values that I'm going to be comparing in my my F test, my Anova test. And what I want to see, which I'm kind of seeing here, is that this guy's bigger. I want to be able to predict more variance than I'm getting at random, basically. And if I do, that means it's worth it to kind of create that more complicated or less boring model. Here's what it looks like graphically, walking you through the same things I've just been saying. But the deviation, for each point, the deviation from the total mean is broken up into 2 parts. There's a deviation of the treatment mean from the total mean, which we have over here in part 1. So these lines which are consistent for each place of articulation. And then number 2 is the deviation of the observation from the treatment mean. So I'm making a more complicated model here. So my residual variance is just the deviation of these individual observations from the treatment means or the place of articulation means. So that sucks up a fair amount of variance, at least comparing like how far away these individual points are from the blue dashed line. But this is the residual variance. This is the noise. And these are the predictions. This is the predicted variance over here. Yeah, so again, we're trying to see basically whether these lines over here are consistently longer than these lines over here, whether our predictions are consistently bigger or better than our errors, as it were, which is a nice situation to be in, right? So what this representation assumes is that number one, changing the factor level will alter the mean of the dependent measure in some consistent way. That's a prediction, right? And then for each data point, there's also still a residual error, some noise in the system that is effectively irreducible from the standpoint of analysis, at least based on what independent factors we're considering. So using the factors that we're using for our predictions, we're never going to be perfect. There's going to be still some errors left over. And like if you really wanted to get perfect, you could say, well, I'm going to sort of have a mean here for P number one, whatever that is, like peel. For peel, I'm going to also make another VOT adjustment and then shift this line down another step. And then for the second production, whatever that was, poll or what have you, you might make another adjustment or so on and so forth. But if you did that, then you're going to wind up with like 15 different factors, right? Like 15 different sort of adjustments you make, one for each of these data points. And that's a really complicated model. It winds up being perfect, but at a cost of being not simple at all. So this sort of model of prediction is pretty straightforwardly simple. I just have one factor, place of articulation. It has 3 different levels. So for each of those levels, you make a little bit of an adjustment in VOT. How well does that do over assuming that everything is just random? So I've got a note here about how these errors that are left over, the residual errors, are expected to be normally distributed about the treatment mean. I think I'm running out of time at the moment, but I've got a little slide here, which is a way you can check whether or not the residual errors are normally distributed or not. That's a fundamental underlying assumption of ANOVA, and if that doesn't work, you have to do something else. But called a Kruskal-Wallis test, I believe, is the non-parametric way of analyzing data like this. But I don't have time to play with this at the moment. You can walk through these commands if you want to, but basically I'll let you know that even though the distribution itself of those residual errors doesn't look super normal, it turns out to not be significantly different from normal. So we'll just keep plodding along because I want to get to the punchline here before I have to go in just a few minutes. So the last step of the process is to compare how much variance you can account for by the treatment means versus how much variance is accounted for by the residual error in each measurement. So basically, if the treatment variance is significantly greater than the residual variance according to an F test, then there is a significant effect of that factor on the dependent measure. And I've walked you through this. I've talked to you about this in a variety of different ways, but basically comparing, is our predicted variance bigger than our error variance? Is our treatment variance bigger than our residual variance using an F test? And just a reminder here that variance is called mean square in the Anova paradigm. I'm really going to have to quit because my voice no longer works. But basically, if you think about it in terms of mean square, we're comparing the average variance accounted for by the treatment versus residual error for each data point is another way to look at it. But practically speaking, what you really want to know is how to get this to work. Here's what the setup is going to look like in just a table. And I've shown you this table already in Excel. But what we want to really get to here is this F value. So I think do I have a residual mean square value? Nope. I have a residual SS value. And I'll just plop it in here by dividing that by 12. I'm not remembering that wrong, am I? Yes, thank you. And now we have a treatment mean square value as well. So we'll just say F value equals treatment mean square divided by residual mean square. So my F value is now 9.09. And if you remember way back at the beginning of this lecture, I was talking about like in the F distribution, it's kind of clumped up towards 0 and it spikes high pretty quickly around 1. And then it tails off. It has a very long tail that is much bigger than 1, depending on how many degrees of freedom you have, of course. But basically, we're looking at sort of the high end, that long end of the tail. We want to see, because that's where you'll be if your predicted variance is bigger than your error variance. So to calculate the probability of getting this F value in an F test, you will insert it and the relevant degrees of freedom into a PF function in R. And there's a couple of different ways I can do this. Actually, I'll do it this way. But our F value is about 9.09. And you can see the answer there, but I'll show it to you this way as well. You get a p-value of 0.003951552, so on and so forth. this is smaller than 0.05. So that means that you have a significant result. That means that adding the factor of place of articulation as a predictor for how much VOT you get in Duchamp stops does better than random chance, basically. So we have to discard that model where the mean values for the different places of articulation are all the same, are all equal to each other, and say, nope, we should be predicting different or expecting different values of VOT depending on our place of articulation. That's what a significant value means in this particular case. So this walks you through that as well here. So stop place of articulation does have a significant effect on Duchamp's VOT. And you can kind of think for a moment about what would the case be if this were the opposite result. So if the treatments were not accounting for more of the total variance than the assumed random errors, then basically the treatment assumptions are not doing a better explanatory job than random chance. In that case, you'd have variances which look fairly equal to each other, or you'd have a pretty small F value, right? Something closer to 1 or maybe even smaller than that. Yeah, so in that case, you'd accept the null hypothesis and just say, I'll just assume it's all just random nothingness, because if I try to make the model more complicated than random nothingness, then I don't do any better. So what's the point of sort of taking that costly step of making a more complicated model when I can assume it's all random chance, right? That's Occam's razor again. Take the simplest explanation available to you. But here, we're making a more complicated explanation because it's worth it. We're able to make better predictions of VOT if we assume that VOT is partly dependent on place of articulation. And I wanted to make one point. I think I've got just a couple slides left here. Yeah, so going back to this one, like this command, I'll show you how to do this the easy way before I'm done. But you notice it's 1 minus PF of that F value, and I could do this in R as well. So we talked about this a little bit with that R to Z transformation. But at that point, I said do it both ways. So it's a two-tailed test. And if I look at this without this 1 minus at the beginning of it, I get an p-value of close to 1, which would not be significant. But in this case, we're only going to look at this side. We're only going to do a one-tailed test of the F value here, because the only sort of situation we care about is whether the treatment mean square is bigger than the residual mean square. We want to have a situation where we're predicting more variance than we have error variance, basically. It's not going to be significant the other way around. If we have significantly more error variance than treatment variance, then that's bad still. So we don't want that case. So we don't even look at that option, that tail of the F distribution. And it would, in fact, be pretty weird if you had that case where you had more randomness than whatever your prediction was accounting for. That would be a very bad prediction. But, you know, like I said before, predictions are hard, especially when they're about the future. But just to give you the graphical representation of what's going on here, remember, we have our treatment deviations and our residual deviations. Anova is basically testing whether the lengths of the vertical lines in the graph on the left are consistently greater than the lengths of the vertical lines in the graph on the right. And I think I mentioned that before. What I haven't mentioned is the easy way to do this. After all this math, all this work, all this graphical depictions of everything, you can run the same test by using this command. So this is showing you a model. We're looking at the dependent measure of VOT and the independent factor of stop. And we're seeing, does VOT depend on stop? And instead of using a linear model, an LM command in R, I'm going to use the AOV command, which is analysis of variance. It's a shame that I didn't say ANOVA, but what are you going to do? It's AOV instead. And this is just going to say, give me a summary of what this model tells us. So here's our model, our more complicated model number 2. We're saying that stop makes a difference. And if I hit return, what I see are all those numbers that I put here in this Excel spreadsheet. And it's also going to give us the sort of same terms like degrees of freedom, sum of squares, mean squares. It's going to give us this F value, which is this guy, E7 divided by E6. We've seen that before. It also gives us a P value, and these two dots say that this is definitely significant. at a alpha criterion of 0.01, so on and so forth. Hopefully this all makes sense at this point, even including how to interpret this test. It basically says that yes, stop has a significant, or stop place of articulation has a significant effect on VOT, so I should include that in the model. It's a good predictor of how much VOT we're going to get. We can do a little comparison here before I'm done and say, look at the output of an LM model, a linear regression model with the same sort of connection between the two factors. We've seen this before. I guess I'm just going to say kind of the only thing we get out of here is that's similar is this F statistic. It gives us the exact same output as what we got from the Anova up here. Hopefully you can see that 9.09 and the p-value, so on and so forth. There's some interesting stuff in here, like I'll talk about this later, but the estimate here is the mean value of VOT for K, 107.4. And then for P, this is how much you have to subtract from K to get the mean value of P. So that's a 40.86. And what these stars over here mean is that that P value is different from the K value, and that the T value is different from the K value as well, so on and so forth. We're not going to focus on this so much anymore, though, having walked through that in great detail. And there's going to be other analytical methods that we'll use that will look kind of similar to this. But lastly, I'll say, we could also just easily look at some other factor we haven't considered yet, like does vowel matter to the amount of VOT we're getting in Duchamp's stop production? So does that depend on which vowel he's producing? We can just run the analysis of variance like this and find out that it isn't. There are 5 different vowels in this data set, so it gets 3 observations for each. Long story short, the F value is 0.916. It's pretty close to 1, like I said before. The P value is much bigger than 0.05. So vowel does not matter to Duchamp's VOT values, this vowel column right here. But that's how you do it with a command that's this simple, and that's how you interpret it, looking at sort of primarily these values over here, and the F value being based on what's going on between these two guys. I'm going to stop now. Again, I have to go pick up my child from school. So I will see you guys next time, hopefully in just a couple days, as we do two-way Anova, which is pretty exciting. See you then.